All right. Well, here's our here are our key terms for Monday. And Monday we're going to talk about population genetics and evolutionary genetics, and really continue to build on an understanding of how we do some of these analyses to determine the relationship between a particular genetic locus and the prevalence of disease or incidence of disease. And then towards the latter half of the chapter, we'll start getting into what are the mechanisms influencing these genetic change, and how does natural selection fix those in a population. So, key terms. First one, retrospective studies. These are the most common type of population genetic study in which you recruit people with the genetic illness, and then you also need to recruit a control group, but you're basically studying the difference between people who have already developed the genetic illness and people who have not developed the genetic illness, and comparing them genetically. Now, finding people with the genetic illness is fairly easy. They oftentimes are already seeking medical treatment from specialists, genetic specialists. But finding people that match and building a similar control group is very challenging. And so in some ways it makes this type of study appealing, the prospective studies. So this is where you just recruit a bunch of people to be basically routinely checked on a yearly basis, or sometimes biannual basis, for you basically just assess their health each time they come and get a checkup. And you can, at the beginning of the trial, you log their genotypes, and then you just follow them, sometimes for decades, basically noting the presence of particular genetic illnesses, or things like this. And the nice thing about these studies is, one, while they're long, they tend to be fairly simple, because you don't really worry about who you're recruiting, and you don't worry about trying to match your control group as well as you can to your experimental group. All right, strict versus loose conditions. Strict conditions require that everybody in your experimental group, those with the genetic illness, have the exact same symptoms, the exact same pathologies, and so this can make it a little bit challenging, especially for diseases that influence multiple phenotypes. And then loose conditions allow you to basically recruit anybody with a genetic illness, regardless of the severity or the particular phenotypic expression of that genetic illness. And so intermediate phenotypes, endophenotypes, these are individuals that have the genetic illness but have a reduced pathology. Hardy-Weinberg equilibrium. This is something you've worked with many times before, and we're going to spend some class time on Monday working through some specific problems. How do we use Hardy-Weinberg equilibrium to predict the number of people in the population with this phenotype or this phenotype or that phenotype? And it becomes a very powerful tool for us to use to determine whether or not a particular genetic trait or just the entire character is under selective pressure. Linkage disequilibrium, the problem that we did on Friday, where we're using our chi-squared analysis that demonstrated either linkage disequilibrium, where the genes are too close together to assort independently, or we also said it could have been an epistatic effect. But anyways, with linkage disequilibrium, we can measure how far apart the two genes are, and how likely they are to be inherited as a unit. Correlation coefficient, we also saw this on Friday. This is that R-squared value, and it is a measurement of the variation in our dependent variable that is explained by variation in our independent variable. Association studies, these are the type of studies that we've been talking about over the last couple of weeks, in which you are basically looking for the relationship or association of particular genetic conditions, particular genetic illnesses, and specific loci and specific mutations at those loci. And so in these association studies, you oftentimes find what we call population stratification, and that's where you have certain groups that are more likely to have a genetic illness and are more likely to have a particular genotype. And so you have to remember that because these are comparative studies, you cannot say that this particular genetic condition or this particular genotype causes this genetic illness, but you can find these evidences of population stratification and find instances of significant correlation. The textbook gives a really interesting example to illustrate that you can't say a particular mutation causes a particular trait, and we'll talk more about that on Monday. Odds ratio and relative risk. So when we're talking about the risk of developing a particular genetic illness, we're really concerned with how does your genotype influence your risk for developing a particular genetic illness. And so the odds ratio is essentially the p-value we get when we compare the experimental group with the control group. And so if we're saying, basically your null hypothesis is the experimental group is not any different than the control group. And then you take your data and maybe you compare it using a 2-sample t-test, or you compare it using chi-squared, whatever we're doing, or you compare it using if you're just doing a correlational study or comparative study, you study it basically using some kind of linear regression. If you force it to fit data that aren't truly continuous but are roughly continuous, or use a logistic or logarithmic regression, you're basically looking at your probability of making a type 1 error. That's your odds ratio. That's basically what you would predict is the probability that group is going to develop that particular genetic, or it's directly related to that value, to the p-value. And so I'll show you some examples of this on Monday, and it will hopefully help us to see what we're talking about with this odds ratio. And then our relative risk is basically the probability or the odds of developing a genetic illness in the experimental group divided by the odds of or probability of developing the genetic illness in the control group. And so if the relative risk is greater than 1, it demonstrates that there's some genetic component that's making our experimental group more susceptible to developing the genetic illness. And so again, we'll look at this a little bit more closely on Monday. On Monday, we're going to spend a decent amount of our time dealing with some of the predictive features of some of these. We'll spend some time with Hardy-Weinberg equilibrium. We'll spend some time with linkage disequilibrium, talk a little bit more about the correlation coefficient, and look at this odds ratio and relative risk, and show how the odds ratio is related to our p-value, to our probability of making a type 1 error.